Lesson 6.3 is the properties of trig functions. So we're going to be looking at trig functions as functions. So looking at all their properties and the different things that we can talk about, including starting with the domains and ranges. So here we have our 6 trig functions that we're going to be looking at and the ratios of them. But it gets a little bit confusing because when we talk about domain and ranges, we're not talking about these x and y, because those are the x, y, and r of a specific point on our circle, versus our domain, which is our input of our trig function, which is our angle measurement, and range, which is the output of our trig function, which is the actual ratio. For sine and cosine, there are no issues, especially because radius is what we're dividing by in our trig function, and our radius is never 0. So we can plug in any angle as we go around the unit circle, forward, backwards, any amount of times. And so our domain for both sine and cosine is all real numbers. For sine and cosine, if we think about our unit circle, the biggest and their smallest that they could be, well, for sine, the smallest would be at the bottom of the circle when it's -1, and the biggest would be the top of the circle when it's +1. For cosine, the biggest would be on the right at 0, where it's at +1, and then on the left would be the smallest at pi, which is -1. So the range for both sine and cosine is from -1 to +1. For tangent and cotangent, they're the ratio of your y and your x coordinates, so the output is going to be all real numbers for both of them. There is a restriction on the input though. If we look at both tangent and secant, and we look at the ratios for those, tangent is y over x, and secant is r over x. So our issue is, for those ones, if our x coordinate is ever 0, we can't divide by 0. So any place where our x coordinate is equal to 0 is a domain issue for tangent and secant. And so that would be at the top and the bottom, so all of the pi over 2's. We write this as theta can't be pi over 2 plus k pi, where k is an integer. So that's saying pi over 2 plus any half of a circle, so that would give us all of your over 2's. You want to just think of it as the top and the bottom. All of the pi over 2's, tangent and secant cannot be. For cotangent and cosecant, they're both being divided by y in their ratios, so the domain issues are going to be wherever y coordinate is equal to 0, which is going to be on your right and your left. So it's going to be the integer values of pi, 0, pi, 2 pi, forward and backwards. So we say that theta cannot be k pi, where k is an integer. And again, think of it not so much as memorizing this, but remembering that it's where your y coordinate is equal to 0, which is at any of the integer values for pi. The range for secant and cosecant is the reciprocal of sine and cosine, so think about flipping it out. So it's from -infinity to -1 or 1 to infinity. A major property of all trig functions is the fact that they are periodic, which means that your y values repeat over a regular interval. So there's a specific length of x coordinates that then repeats your whole set of y coordinates over and over again. So what that means is that your y coordinate at some angle plus whatever the periodic value is, p, is going to be the same as your y coordinate at just the original angle theta. For all of the trig functions except for tangent and cotangent, the period is 2 pi, which means that every 2 pi, sine, cosine, secant, and cosecant repeat. For tangent and cotangent, because they're the ratio of the x and y coordinates, they actually repeat every pi. So every half of a lap around, the tangent and cotangent values repeat. So we can use these rules to help us evaluate trig functions when the angle measurement is either bigger than 2 pi or smaller than 0. We can use these periodic values to help us out. So for the first one, we have sine of 17 pi over 4, which I notice is bigger than 2 pi. So 17 pi over 4 is bigger than 2 pi, so I want to take out one full rotation to see if I have something that I recognize on my unit circle. So 2 pi, one full rotation with a denominator of 4 would be the same thing as 8 pi over 4. So if I take that out, I'm left with 9 pi over 4. So I know that the thing went all the way around the circle once. Now I notice that 9 pi over 4 is still bigger than 2 pi, which means it went all the way around the circle again. So I took another 2 pi or 8 pi over 4 out. So this thing went around the circle twice. And then I'm left with pi over 4. So it went all the way around the circle twice and then ended at the same place as pi over 4, which means it shares the same coordinates as pi over 4, so the sine of that angle is going to be the same. So the coordinate at pi over 4 is root 2 over 2 root 2 over 2. Sine is y over r, where your radius is 1 on the unit circle. So we end up with that the sine of 17 pi over 4 is the same thing as the sine of pi over 4, which is root 2 over 2. So go ahead and pause the video and try the cosine of 5 pi and the tangent of 5 pi over 4. So for cosine of 5 pi, I noticed that it's bigger than 2 pi, so I took a 2 pi out and I was left with 3 pi, so it went all the way around the circle once. And then I noticed that 3 pi is still bigger than 2 pi, so I took another 2 pi out, so it went all the way around the circle twice, and then I was left with pi. So it went all the way around the circle twice and ended at pi, so the cosine of 5 pi is equivalent to the cosine of pi, which is -1. The tangent of 5 pi over 4, now 5 pi over 4 is one that we already have on the unit circle, so if you just evaluated this regularly, that would totally make sense. But tangent has a period of pi, which means it repeats every pi instead of every 2 pi. So if I take a pi out, 4 pi over 4, I'm left with pi over 4, which means that the tangent of 5 pi over 4 is equivalent to the tangent of pi over 4, which is 1. So using these periodic properties to help us realize that no matter how many times you go around the circle, you end up ending at the same location, which means your ratios are going to be the same. Here's just a bunch of properties for trig functions. So the first ones are reciprocal functions, so all of the ones that are reciprocals of each other. So sine and cosecant are reciprocals of each other, so the sine of theta is equal to 1 over the cosecant of theta. Cosine and secant are reciprocals of each other, so cosine of theta is 1 over secant of theta, and tangent and cotangent are reciprocals of each other. Our quotient identities, because tangent is y over x, it's the same thing as y over r over x over r, so it's equivalent to sine divided by cosine. Cotangent is the reciprocal of that, so therefore it's the same thing as cosine divided by sine. Our Pythagorean identities, so this is something based on the Pythagorean theorem, so we have sine squared plus cosine squared is equal to 1. So it comes straight from the Pythagorean theorem. Sine is y over r, cosine is x over r, so you have y over r quantity squared plus x over r quantity squared is equal to 1, which says that y squared over r squared plus x squared over r squared is equal to 1, which is x squared plus y squared equals r squared, Pythagorean theorem. The other two Pythagorean identities are derived from the first one using the reciprocal and quotient identities. So if I take sine squared plus cosine squared equals 1 and divide everything by cosine squared, sine squared over cosine squared is tangent squared, cosine squared divided by cosine squared is 1, and 1 over cosine squared is secant squared. Same thing if I take all of these and divide them by sine squared, sine squared divided by sine squared is 1, cosine squared divided by sine squared is cotangent squared, and 1 over sine squared is cosecant squared. So a lot of times I just say memorize the first one and then know how to derive the other two. Even and odd properties, cosine and secant are even, which means that the cosine of the opposite of theta is equivalent to the cosine of theta, so they're reflexive across the y-axis. And then the other four are all odd. So f of negative x is equal to negative f of x, so sine of the opposite of theta is equal to the opposite of sine of theta.
So we can use these properties to evaluate trig functions when we're given trig functions instead of coordinates. So for example, they tell us that sine of theta is root 5 over 5 and cosine of theta is 2 root 5 over 5. So go ahead and pause the video and use the properties to find the other four trig functions. So tangent of theta is the same thing as sine divided by cosine, so root 5 over 5 over 2 root 5 over 5, or 1/2. Cotangent of theta is cosine over sine, so 2 root 5 over 5 over root 5 over 5, so it simplifies down to 2. Secant of theta is 1 over cosine, so 1 over 2 root 5 over 5, which is 5 over 2 root 5, or root 5 over 2. And cosecant of theta is 1 over sine, which is 1 over root 5 over 5, which is 5 over root 5, or just root 5. So using those properties to help evaluate those trig functions. So same thing down here, you can evaluate these expressions. Even though we don't have 20 degrees is one that we have memorized, we can use trig properties to evaluate these expressions without a calculator. So go ahead and pause the video and try these. So for the first one, sine of an angle divided by cosine of an angle is the same thing as tangent of that same angle. So you end up with tangent of 20 degrees minus tangent of 20 degrees, which is just 0. For this one, 1 divided by secant is cosine, so 1 divided by secant squared is cosine squared. And then sine squared of an angle plus cosine squared of the angle is equal to 1. Sine is odd, so sine of negative 45 degrees would be the same thing as negative sine of 45 degrees. So then the sine of 45 degrees is root 2 over 2. You end up with negative root 2 over 2. The last thing is that we can use what we know about the different trig ratios to figure out where we lie in the coordinate plane. So for example, if we know that sine is negative and cosine is negative, we can figure out what quadrant we specifically live in. So if sine is negative, that means that my y over r ratio is negative, and r is a distance, so it's always positive, so therefore my y coordinate must be negative, which means we must be in either quadrants 3 or 4. And if cosine is negative, that means your x over r ratio is negative, and again, r is always positive, so that means your x must be negative as well, which means you must be in quadrants 2 or 3. So if you have to be in quadrants 2 or 3 and in quadrants 3 or 4, therefore you must be in quadrant 3. So we can use that idea for a problem like this, where they give us that one of our ratios, sine of theta, is equal to 1/3, and they tell us that cosine of theta is negative. So we have enough information to know what quadrant we're in, and then find the other 6 trig functions. So they give us that sine of theta is 1/3, which is positive, so that means our y coordinate must be positive, and they tell us that cosine is negative, which means x must be negative, so if we have a negative x and a positive y, we have to be in quadrant 2. I know that the ratio for sine is y over r, so since this is not one that I recognize from the unit circle, I'm not going to assume it's on the unit circle. So I'm going to say that my y coordinate is 1 and my radius is 3. So then I need to use Pythagorean theorem in order to find my x coordinate. So I use Pythagorean theorem, x squared plus 1 squared equals 3 squared, so therefore x is equal to negative 2 root 2. I know it's negative because they told us that cosine is negative, which means x has to be negative. So now I have enough information, go ahead and pause the video and find the rest of the 6 trig functions. So cosine of theta is x over r, so negative 2 root 2 over 3. Tangent of theta is y over x, so 1 over negative 2 root 2 or negative root 2 over 4. Cotangent of theta is x over y, so negative 2 root 2 over 1 or negative 2 root 2. Secant of theta is r over x, so 3 over negative 2 root 2 or negative 3 root 2 over 4. And cosecant of theta is r over y, so 3 over 1 or 3. So this section has all been about the properties of trig functions and utilizing the properties of trig functions to evaluate.